Are there any questions?
Just a quick one about, a while ago on 1B, we had those 4 graphs with capacitors and resistors.
Right.
I know resistors slow down the current. Do capacitors just speed up the current?
No, the capacitor will, when it first starts out, it's as if the capacitor's not there.
Mm-hmm.
So charge will flow as fast as it can across that. But as soon as you get a charge on there starts to be, resistance is not officially the right word, there starts to be a repulsion for more charges getting on there. So the more charge that gets on the capacitor, the harder it is to get charge on the capacitor. So what a capacitor should do, and a spoiler for some of it, if it's just a capacitance circuit, wrong junction. So you make the connection, charge quickly goes up, and then as the capacitor starts to fill, it becomes harder and harder. And so eventually, it goes to 0. Is that good for you?
Yeah.
Well, it's physics, so of course it's good for you. But does that answer your question?
Yes. I left my pencil on my desk.
You left your pencil? Dixon Ticonderoga or Sloan Academics?
The first one.
It even has an eraser.
Very excited.
We're just spoiling you here.
So touched.
Other questions?
Might not be totally related, but a light year, why is the light year called a light year?
It is the distance light travels in 1 Earth year.
So like it's the speed of light relative to 1 Earth year?
Yeah, so it'd be speed of light times 1 year. And then make sure the units work out.
Okay.
So something that's 4 light years away, that means that, in essence, light from the sun takes 4 years to get there. From Earth's point of view. From light's point of view, how long does it take to get there?
No time.
Week. All right. The Lorentz transformations I just sort of presented up to you. I am going to do one derivation. Half of it can be done very quickly. The other half takes more tediousness, so I'm just going to do the first half. Sort of more of the exploration of things really what you think they are. All right, so Earth, which I will call the S frame. And then I've got a rocket. Which I would call the S prime frame. So I have a rocket that's zipping by Earth, and at the moment that it's passing Earth, at the moment that the origins of both systems are on top of each other, or at least the X coordinate. So when X equals X prime equals 0, so we're talking this point right here, that point right there, line up, we synchronize the clocks. So at that moment, therefore at that moment, t equals t prime equals 0. In whatever unit you like. There is an event that will happen out here. We will call this, I will call this point H. For happening. Something will happen there. So at that moment, when x equals x prime equals 0, and that then we synchronize the clocks, there's an event that's going to happen over there from Earth's point of view at the point x 0, and that is position and time. I guess x sub h. And from the rocket's point of view, that's a comma, not a prime. Comma. X, H, initial, comma, 0, prime. X prime, H initial. Now the reason why it's H, I have initial for the rocket, not for the Earth, is that the distance from Earth to where this point in space is pretty much constant. So the initial and the final value are the same. The distance to H is basically, this distance right here would be the proper length, because that distance is the distance when both objects are at rest. And from the rocket's point of view, the distance from here to here, that's x, h, initial, prime. But when something happens here, the rocket will have gotten closer to it. Or from the rocket's point of view, the event will happen closer to the rocket. Because of length contraction, this position right here would be gamma, x, h, initial, prime, comma, 0. And we derived the length contraction formula earlier. All right, so after some time t, or t prime, a light flashes at h. So when the rocket is here, and I can get a better marker than that. Yeah, there we go. When the rocket is here, light flashes. So that distance right there would be x, h prime final. And so light flashes at h. From the Earth's point of view, at the position x gamma, x h prime t, and from the rocket's point of view, x h prime final t prime. All right, so let's take a look at the two different points of view. That's just labeling so far. All right, so for the Earth's point of view, the rocket has traveled, so that distance right there would be however fast the rocket's going, times time, t. That's the time from Earth's point of view. And so this distance from here to here should just be, well, the initial distance to the happening minus dt. Bless you. And then from the rocket's point of view, h is moving towards the rocket. The distance that h, probably better if I just did a different diagram. So from the rocket's point of view, the rocket hasn't moved. That distance there, the initial distance was x h prime initial, And the rocket basically is moving some speed v t prime.
You mean the H?
What?
The happening is moving some speed v2,
Yes, what did I say?
the rocket.
Okay, yes, the happening. The planet, the distance, whatever this point in space is, it's heading towards the rocket at speed v. They agree upon v. Earth and the rocket agree upon something's traveling at that speed. They just disagree with what. So this distance here would be x h initial prime minus vt prime. Meanwhile, the Earth is traveling back that way, and so I guess that distance right there would be vt prime as well. So we have, from the rocket's point of view, Earth and that point in space are moving to the left. So x prime h initial is equal to actually, let me change that. X h final prime, which would be this distance here, is equal to x h initial prime minus vt prime. So, however close the rocket is to that point in space is just equal to the difference. From that, if we solve for x h initial prime, that's just x h final prime plus vt prime, which, because of length contraction, as established over there, is equal to x h over gamma. I did xh prime equals, sorry, I did xh equals gamma xh prime, and so just divide by prime, the gamma. And so therefore, xh, the distance from an Earth's point of view is equal to gamma times xh final prime plus vt prime. And that's one of the Lorentz contractions. Now, when we did it before, we had a negative here instead of a positive, but we're looking at it from a different point of view. This is the rocket over here and the Earth over there, and before we had flipped it around. So anyway, that's one of the Lorentz contraction formulas. If I did the time one, it takes time.
So, will we have all of those formulas on the quiz?
Yes. And as before, I recommend doing the Galilean relativity, just figure out if that's plus or minus. Just figure out what it would be if you didn't have to worry about relativity, and then throw gamma in front. Excuse me. How much do I have to leave there? All right, there's a little bit of calculus in this. I think that it is not so bad, considering some of the stuff that we've done already.
Something like derivative here, derivative there, what you gonna do about it?
Yeah, it's a slope. Or an antiderivative is, you're trying to figure out what would have a slope that creates the graph.
Something like
Good. Questions? Just don't tell Ethan. All right. There is one bit that I am definitely skipping over. It is the longest part of any derivation that we would do. And so, speed of light's the same in all reference frames, dot, dot, dot. M equals gamma M sub naught. So that dot, dot, dot fills in. The first time I did it in front of a class, fills in about 2 hours worth of math. I have found simpler ways of doing it, but still, that first time was, may God have mercy on their souls. All right. So we're going to start out with this concept right here. This is relativistic mass on the left-hand side, and the right-hand side, this is the rest mass. So on the right-hand side, this is the mass of an object when it is at rest, when you are finding this mass, when it is at rest relative to you. Such as every time you use a triple beam balance, you're finding the rest mass. Now, there are some who claim that the mass is not relativistic, but it's the momentum. So if I multiply both sides by the velocity, we'd end up with P is equal to gamma P sub naught. I have not found a case where this is not really, you can't use this. And part of, I did read one place that it depends on who your teacher was. So that the older generations tend to look at relativistic mass, whereas the newer ones tend to look at relativistic momentum. So there'll be a transition at some point. All right, so work. Question?
Is this still unit 28? Or-
Yeah, we're doing relativity still.
Okay.
Work?
Negative change in potential? Or? Oh. Changing kinetic?
Okay, total work. Which version do I want? I think we'll go with the change in kinetic. It's not what I want. Try that again. These are vectors, but I'm just not going to write it out of tradition. Momentum.
Mass times velocity.
Impulse. Dusting off those cobwebs here. Impulse.
Moment of inertia. Nope. Mass times displacement.
I'm trying to think mass times displacement, that's nothing in particular right now.
Mass times acceleration.
That would be force. All right, we can start there.
The change in momentum?
Yeah, we'll go. Changing momentum. So if I have impulse, is the change in momentum. Guess I'm now putting vector symbols on it. And momentum is mass times velocity, so we have the change in mass times velocity. And this question at what point do I hand wave? And velocity. Wait, that's not what I want to do there. I want to, up here, acceleration.
Change in velocity over change in time.
If I multiply both sides by time, I get force times time is equal to mass times change in velocity. Little bit of a hand wave there, equals change in mass times velocity, which equals change in momentum. In other words, impulse is either force times time or it's change momentum. So we can define force as the change in momentum over the change in time. If I multiply both sides by the change in position, and just shift my delta t over, so I have force times the displacement on the left-hand side. And what's force times displacement?
Velocity.
No.
Speed.
No.
Force. Oh, force times displacement.
Yes.
Moment of inertia.
You're just throwing out words from the last semester. Let's take a look at the units. What are the units of force? That was said with incredible enthusiasm. Once more with feeling. Units of displacement?
Meters.
Newton meters, also known as?
Joules.
Joule is a unit of?
Energy.
Energy, yes, but the other one?
Work.
Actually, energy is the one I want. So what I have over here is